Hello everyone. So up till now we have seen the optimization of a multivariable function, and from today we are going to study about the optimization of multivariable function subjected to constraints. Okay, so up till now we have seen uh, the optimization of multivariable function, that is a function that is dependent upon more than one variable, right? We have seen that the function fx is dependent upon two variables, that is x1 and x2. The equation had two variables, right? But the function fx was not restricted by any other parameter, right? We had a simple equation and we have to optimize that equation. But what if there is a constraint to that equation, right? By constraint we mean that some other form of restriction, right? This restriction can be in the form of equality. This restriction can be in the form of variable having greater or equal to some other function, or should be in between a function, right? So if such kind of constraint is available, then optimization has to be done in such a way that maxima or minima of a point has to be find out where that maxima point or the minima point satisfy the constraint also. Okay, so for that there are number of methods available to optimize a multivariable function that is subjected to constraints, right? And among that uh, we are going to study few of those, and in this the first method that we are going to study is Lagrange multiplier method. Okay, so your Lagrange multiplier method is one of the methods that is used to optimize the multivariable function that is subjected to some constraints. All right. So in the Lagrange multiplier method, the strategy is to find out the maxima or minima of a function subjected to equality constraint, right? So this means an equality constraint is available to the multivariable function, and so if this equality constraint is available, so we can apply the Lagrange's multiplier method and optimize the equation, right? And basically in this what happens is that the constraint problem is converted into a derivative form, right? And that derivative form satisfies the unconstrained optimization criteria. Okay, now in this what happens is that there is a Lagrange multiplier function, right? That is denoted by lambda, right? And suppose we have a equation that is f x1 x2, that is the equation has two variables x1 and x2, right? And in this equation we have a constraint in the form of g x1 x2, right? So our basic equation is f x1 comma x2, right? And in this there is a constraint. This constraint is again is in the form of a equation that is represented here as g x1 comma x2, right? Now in the Lagrange multiplier method what happens is this constraint is also involved in the equation, that is a new equation is formed using Lagrange multiplier, right? So in your function in your basic equation, that is f x1 x2, using the Lagrange multiplier function we involve the constraint and form a new equation, that is L x1 x2 and lambda, right? So this new equation is now dependent upon the variable x1, x2 and lambda, right? So we have three variables that are dependent for the Lagrange's equation, right? Now depending upon the constraint that is available, so suppose right now in the equation we had only one constraint. If suppose we have another constraint, let's say this is let's say the constraint is g1 x1 comma x2 and g2 x1 comma x2, right? So now we have two constraints, right? So what will happen is more Lagrange multiplier will be added and the equation will be formed. Okay, so fx, that is this is our main equation that we have to optimize, right? And depending upon the constraint, so suppose we have more than one constraint, we have g1 constraint, we have g2 constraint. So using more Lagrange multipliers, that is lambda 1, lambda 2 and so on, we will form a new equation and then we will do the first derivative of that to find out the values that will either give the maxima, minima of the function, right? So the necessary condition is that the new equation, that is Lagrange's equation, will be differentiated, will be partially differentiated with respect to the variables that we have, right? So if we have x1 and x2 variable, right, then this Lagrange's equation will be partially differentiated with respect to x1, x2 and lambda, right, because the new equation also has a lambda parameter. So partial differentiation with respect to the number of variable involved will be done, and through this we will find out the solution of the equation. That is, we will find out the value of x1, we will find out the value of x2, and we will find out the value of lambda. So these values will give the maxima, minima, or a point at which we will either have null point, right? That is, neither have maxima, minima of the point, right? So through this we'll get the number of points, and we'll see if these points have the maxima or minima, or neither maxima neither minima. So this is the necessary condition, right? So through this we'll find out the points, right? To ensure that the obtained point have the maxima or minima, or it is a null point, that is neither we have a maxima nor minima, we need to satisfy a sufficient condition. So for that, what we'll do is we'll prepare a matrix, right, and through this we will add a polynomial function to the variables involved, right, and we'll find out the value of the variable, and if the value of the variable is negative, then we have the minima, and if the value is positive, then we will have the maxima. Okay. So to find out the, or to form the matrix, what we have is we have the let's say we want to obtain the coordinates of the matrix. So for that we'll differentiate with respect to the variables that are involved. Okay, so if we have let's say Lij, right, we have Lij, so the equation shall be differentiated with respect to day over xi and day over xj, right, where xi and xj are the coordinates of the matrix. All right, likewise the constraint is also need to be differentiated, and in that, if we have the constraint gpq, the coordinate, then respective differentiation has to be done. So if we have gpq, then differentiation has to be done with respect to q. All right, so if the obtained polynomial value, after solving this, if the obtained polynomial value is negative, then we have maxima, and if the value is positive, then we have the minima of the function. Okay, so this is how the Lagrange's method is done, right? So let's do a numerical for better understanding. Okay, so we have a question that we have to minimize the function subjected to x1 plus x2 equal to 5, right? So in this is our objective function, right? This is the objective function, right, while this is our constraint. Okay, this is our constraint. So we have to find out the points that will give us the minima of the function while satisfying this constraint value. All right, so let's do the solution. So the first thing is that we have to form a Lagrange's equation, right, and in that the constraint is also involved using the Lagrangian multiplier lambda, right? So the new equation L x1 comma x2 comma lambda will be formed using minus 3x1 square minus 6 x1 x2 minus 5 x2 square plus 7 x1 plus 5 x2, right? And as we have discussed, there will be a Lagrangian multiplier lambda, right? with followed by the constraint equation. Okay, so we will have plus Lagrangian multiplier lambda followed by the equation x1 plus x2 minus 5. Okay, so this is our Lagrange's equation. All right, the next thing that we have to do is we have to do a partial differentiation of this equation with respect to the variable of the equation. So we have three variables, we have x1, x2 and lambda. So we are going to differentiate this equation with respect to x1, with respect to x2 and with respect to lambda, right? So let's do the partial differentiation. So d over L by d over x1, right? So on partial differentiation we'll have minus 6 x1 minus 6 x2 minus, so this term will be treated as constant and that will be equal to 0, right? Then we'll have plus 7, right? Again, since no x1 variable is there, so it will again be 0. All right, then we'll have plus lambda, right? Lambda x1, on partial differentiation of lambda x1 we will get the lambda. First lambda x2 minus 5 lambda, again since no x1 variable is there, so it will be treated as 0, right? So through this we have obtained our first equation, right? We'll put this equation equal to 0, right? This is our first equation. Then differentiating with respect to the second variable, and that is x2, right? So differentiating with second variable, this will be treated as constant since no x2 is there, so it will be 0. Here we'll have minus 6 x2 minus 10 of x2, then we'll have 5 plus lambda equal to 0, right? So this is our second equation. Then the third variable is lambda. So differentiating the Lagrange's equation with respect to the derivative lambda, and we'll see that we'll get only this equation. So this is equals to x1 plus x2 minus 5 equal to 0, right? So now you observe that we have three equations and our unknowns are 3, right? x1, x2 and lambda. So three equations, three unknowns can be solved very easily. You can either solve it manually, but since we have the facilities in the calculator, so we should use the calculator to solve these three equations, right? So if you have 991 ms calculator, so in 991 ms calculator, what you have to do, you have to press mode 3 times, right? Then you will see it will show the eqn sign, that is equation sign. So you have to, and below it will return 1, so you have to press 1 for equation, that is eqn, right? And then you will see it will ask for number of unknown, right? You see that it asks for the number of unknowns in your equation, and here we have 3 unknowns, right? So we'll press 3, right? We'll press 3. Okay, so now is if you've done everything right, it is going to ask for a1, a2, a3, or a, b, c, right? Something like this. It will ask for the all the variables a, b, c, this one c and d, right? And it has to just make sure that the input data are in the form of a x1 plus b x2 plus c x3 is equals to d, right? So this is your x1, a x1, b x2, c x3, right? So the d variable in this case will be minus 7, right? It should be taken here and it will be minus 7. Likewise this d is minus 5, all right, and here it will be plus 5. This need to be taken care of while putting the values. Okay, so if you put the values, right, the calculator will give you the values of x1, x2 and lambda. right, in the form of I. So the values that we will get, the x1 will be 5.5, x2 will be minus 0.5, and the value of lambda will be 23. Okay, so the value of lambda will be 23. All right, so we have find out the values of the equation, right? So we have x1 equals to 5.5, x1 equals to 5.5, x2 equals to minus 0.5, and lambda equal to 23, right? So to see at this point we have the maxima of the function or the minima of the, like this point, what do we have? Either we have maxima or minima or nothing. For that we have to uh, check through the sufficient condition, right? So what we are going to do, we are going to apply the sufficient condition. Okay, so we are going to apply the sufficient condition. So for that we are going to prepare the matrix, and since we have two variables, so uh, first of all we will find L11 coordinate, right? And your L11 coordinate, that is Lij. Lij in this case is L11, right? So this means first of all you have to differentiate with respect to x1, then again you have to differentiate with respect to x1, right? Lij in this case is I is 1 and j is also 1, right? So first of all you have to differentiate the equation with respect to x1. Again in this case j is also 1, so again you have to differentiate with respect to 1. Okay, so L11 will be d over square L divided by d over square x1 or d over 1 x1 square, d over x1 square, right? And we have already differentiated in equation 1 first time. This is our equation, right? We have already differentiated in the first time, so we are again going to differentiate this equation again, right? So on again differentiating, what we will have, we will have value to be minus 6. Okay, the value will be minus 6. Then we have L12, right? L12, that is Li is 1, j is 2. This means first of all differentiate with respect to x1, j is 2, then this means differentiate with respect to x2. Okay, so what we are going to do, we are going to differentiate the equation first of all with respect to x1, then with respect to x2. Again in the equation 1 has already been differentiated with respect to x1. Now what we are going to do, we are going to differentiate again this equation with respect to x2, right? So let's differentiate this equation 1 with respect to x2, and you will see, since only this has x2, right, so everything will be treated as constant and will be 0, right? So the value will be again minus 6. Okay, right, this is our L1, L11 and L12, right? Now we're going to find L21, L21, right? L21, this time I is 2 and j is 1. So first of all differentiating with x2, then differentiating with x1, right? And here you see we have already differentiated with respect to x2, right? So we are going to differentiate equation number 2 with respect to x1, right? And if we differentiate it with respect to, I think this, what there was, this is minus 6 x1, right? So this will be minus 6. Then L22, for L22, this means we have to differentiate the equation number 2 with respect to d over x2, right? So on solving or double differentiating with respect to x2, we'll see the value comes out to be minus 10, right? The value comes out to be minus 10. Okay, so these are the parameters. Now in the equation we also have g11 and g12, right? So one thing that you should note is that while L11 and L12 are arranged in this way, your g11 and g12 are arranged in this way, right? And since in this equation we have only one constraint, right, that is we do not have the second constraint, so we will not be using all these parameters, right? So these are of this will not be used in this equation, all right? So we will have only g11 and g12 here. Okay, so for g11, right, g11 means that the equation has to be differentiated with respect to q, that is d over x1. Okay, so differentiating it with respect to d over x1, right? So our g was x1 plus x2 minus 5, right? This was our g. So on differentiating it with respect to x1, we will have the value to be 1, right? You, right, then we have g12. G12 means differentiating this with 2, right? Differentiating it with 2. Okay, so differentiating it with 2, the value will be 1. All right, so we have the coordinates. Now what we'll do is we'll form a matrix, so that it, and we'll add a polynomial, right? So the matrix has to be formed in the form of L11 minus polynomial function, then L12, then G11, L21, L22 minus polynomial function G21, then we have G11, G21 and 0. Okay, so forming it like in the same format, so our L11 is minus 6, right? So this will be minus 6 minus the polynomial function, then L12 is again minus 6, so it's again minus 6, then we have 1, then again it's minus 6, then minus 10 minus the polynomial function, then 1, then 1, 1 and 0. Okay, so we are going to find out the determinant, and I'm solving it. So what we are going to do, so first of all, we are going to have minus 10 minus the function into 0, sorry, so we'll have minus 6 minus the polynomial function minus 10 minus the function into 0 minus 1 into 1, right? Then we'll have minus, we'll go to the second, so again since we are going here, so this will be minus of minus 6 into 0, minus 6 into 0 minus 1 into 1, 1 into 1, then again minus, so this time we'll have this, so 1, So we'll have minus 6 into 1 minus 6 into 1 minus 10 minus 8 into 1, right? So this will become 0. So we'll have minus 6 minus the polynomial function into minus 1 minus 6, this is 0, into minus 1 into minus 6 plus 10 plus equal to 0. Okay, so on solving it, we'll have this value to be minus 2, right? So since it is negative, so since the polynomial function is negative, the value obtained, that is at x1, x2 and lambda, these value obtained corresponds to maximum, right? This corresponds to maximum. Okay, so this is how we solve this Lagrange method. Okay, so right now we have two polynomial function. If we had more than like two, like x1, x2, x3, x4, so in this case the values of these variables comes out to be more than one, right? So right now if, like we have the value of x1 to be 5.5 minus 0.5 and 23, so we can have multiple values, right? So if on applying the sufficient condition we have both positive value and negative value, that means that we have neither maxima nor minima, right? If we have the negative value of the polynomial function, then it is maxima. If we have uh, the positive value of the polynomial function, this means that we have minima of the function. Okay, so this is how we solve the multivariable functions subjected to equality constraint using Lagrange multiplier method. Okay, so try it yourself. If you have any doubt, we can discuss. Okay, so that's it for today. Thank you.